Okay, so this is problem 1240 on page 485 and 486. The figure is on page 485, so you want to reference that page. But then page 486 is where the problem statement is given. It references the figure and says that it shows a drive for a system to crush coal and deliver it by conveyor to a railroad car. Gear A delivers 15 kilowatts to the crusher, and Gear E, delivers 7.5 kilowatts to the conveyor. All power enters the shaft through Gear C. The shaft carrying gears A, C, and E rotates at 480 RPM. Design the shaft. The distance from the middle of each bearing to the middle of the face of the nearest gear is 100 millimeters. Okay. They've given us a figure, it's in the book, but I'm going to copy it down to some extent because it'll be useful in our discussion. So let me just draw the shaft here and put the different sections on it. So we've got gear A here. B is a bearing. Now you'll recognize the bearings because they usually have a cross on either side or an X on either side to indicate that it's a bearing. Gear C is in the center essentially. Gear, or not gear, but bearing D is off to the side here. And then E is near the end. Now I've drawn A and E at the very ends. The reason for that is because anything beyond those doesn't have any load in it, and so it doesn't matter what we do there. So really the only section of the shaft that we want to analyze is this. Now for practical purposes, since A has to be slid onto the shaft, what you would typically do is make the size on this side of A be slightly smaller just so that it's easy to slid it on. Yeah. Yeah, well, usually on a shaft like this, you wouldn't have a press fit. You'd have keys or you'd have barrier hooks or something to lock it to the shaft. But I drew all of this because I wanted to make some notes. Let's see, it says that Gear A delivers 15 kilowatts to the crusher. So Gear A, we've got 15 kilowatts coming out of it. But then E delivers 7.5 kilowatts to the conveyor. And the reason for doing this is so that you can see we should just add the two and get the total amount of power come in a C. Now, would all of the power that comes in C go out at E and A? No, there'd be a little bit of loss, but in a shaft it's not much. There's a little bit of loss mainly in the bearings and in the gearing, but it's not worth talking about for our purposes. So if we add 7.5 to 15, then what that means is that we've got 22.5 kilowatts coming into the shaft. And that'll be important a little bit later. We'll need to know that. Did I add that right? 7.5? Yeah, that should be okay. All right, questions so far? All right. Now, I want you to refer to the figure because what we really have to do is figure out all the loading on the shaft. And the reason we have the bearings here is because there is load from the bearing. Remember, the bearings are there and there will be reaction loads. So we have to take that into account. Now, those are shear loads. There's no torque load due to the bearing, so the torque from C to A would be constant, and the torque from C to E would be constant. Yes, there's a little bit of friction load, but when we're talking about this scale, it's negligible. We don't worry about it. That's kind of interesting. This kind of looks like a crankshaft in your car, except of multiple bearing points. It's interesting that you actually lose a couple of horsepower so per bearing when your engine's at full speed. As the speed goes down, the power you lose decreases, but as the speed goes up, the power loss increases. But that's a plain bearing. We will talk about plain bearings as well later. So anyway, what we really need to know is all of the loads in the shaft at all these points. Really, that's our first order of business, is figuring that out. And so basically, we're going to start with the fact that we've got spur gearing at A, C, and E. Put this over here. That's not very good. Let me try again. There we are. Okay, so what I've drawn here are the gears that are on the shaft. I've tried to put them in line so that you can see that these are all the gears that are on the shaft. Okay, the other gears, the mating gears, are off of the shaft. So the mating gears are Q to gear C, S to gear E. I don't have room to put E on the gear, or A. A is on the shaft, but its mating gear R is not. Okay? Now, why did I draw all these? Well, I need to consider the direction of force. Now, they've shown us that Q is rotating in this direction. Now, here's what gets confusing. You know how in statics you had to figure out free body diagrams and forces and all those things? What could be confusing is that you always needed to find forces on the body. We need to find the forces on the shaft. So what we're going to start with is find the forces on gear C, A, and E. Okay, that's what we're going to begin with.
It says all pressure angles are 20 degrees for all gears. So
Well, it depends. There's actually two different. You say it says in this case. Okay, yeah,
So-
yeah, that's important. You're right. Thank you. So we'll have to use that information a little bit later. But for right now, let's figure out what direction the forces are on these things. Okay, so if C or Q is turning this way, then it would be pushing this way on C. Does that make sense? So let's draw all those loads on. And understand, I'm drawing the load from the gear onto C. Okay, the load on Q would obviously be in the opposite direction. Now help me figure out on this gear, on A. Well, let's see. If Q is turning this way, then A is also turning clockwise, right? But there's resistance from R onto A. So the direction of the force on A should be in the opposite direction. This is turning this way, right? But we're interested in forces on A. Remember, R is resisting. Think of R just sitting still.
yeah.
Okay, then R is going to push in this direction to try and keep A from rotating. Yes?
I just have a hard time trying to picture it. That's when you cut those.
Yeah, because it's
Uh,
We're not necessarily cutting the gears, we're just looking at them. and-
No, like the picture. That's when you.
This is looking at the gearing from the side. So if we were to take this gearing, turn it, and lay it down so we can see it.
Okay.
That makes
so you
sense?
took the shaft from this way and turned it this way.
Okay, that's
So
what.
turning the shaft
Yeah.
90 degrees.
Okay, yeah.
Okay, so you guys tell me, how would the loading be on E? To the right or to the left?
Did the same.
Same as?
A.
That's right. It'd be the same as that. Does everybody understand that? It's okay if you don't, we can talk about
So
it.
E would be turning this way.
Well, think about it, they're all turning this way, because we're gonna look at them from a consistent direction. We've already looked at Q from, I don't know if it's this direction or this, it doesn't matter, right?
Right.
But we need to be consistent. I see frowns.
It's hard to conceptualize.
Yeah, I just
Yeah.
I thought I had it, now I don't.
Yeah, here's the key. You're looking for forces and loads on the gearing that's on the shaft, okay? You need to know what direction they turn first of all. Q is driving C, but A is driving R.
I
Q
don't
is off the
agree.
shaft, C is on the shaft, and that's what makes the loads reverse direction.
I don't agree with the direction they're turning.
The direction that A and E are turning?
Yeah, well, if Q is turning this way, C would be turning the same direction.
You're right, you're right. C would be turning in this direction.
Yeah, I
You're
mean-
right, so I've got those backwards, thank you.
I'm just like, this doesn't make sense
You're
anymore.
right. Yeah, you're right. So they would be turning counterclockwise since C would be turning counterclockwise.
And the
Okay.
force on
So
the
now the
shaft
force is
would
gonna
be
be in the opposite
backwards.
direction,
Yeah.
right?
Okay, cool.
Now, here's where it can become confusing as well. Notice there's another difference here. It just so happens that all the forces are to the left on A, C, and E, but if your R were above instead, that would change the direction as well. So, thank you guys for keeping me straight. Okay. So there are the part of the loads. Now, there's always that 20-degree pressure angle, and so there will also be a force trying to separate the gears. There will be a radial force, and that force will always act towards the gear that we're looking at it at. Does that make sense? Okay, because it's trying to pull the two apart. Okay. So what we need to do is come up with the magnitude of all these forces. Now, how do we do that? Well, what you have to do is use an equation that's in the book. Rather than going through my notes, let's just go through the book because that'll be the easiest way to go. Everything you need is in chapter 12. And let's see, sometimes you have to dig for it. So what you'll probably want to do is make a note of the equations that are especially useful, and maybe even tab some of the pages. So if you go to page 455, you'll see two equations that are going to help us out quite a bit. There's equation 2 and equation 3. Equation 2 says that the tangential load, W sub t, which notice these are all W sub t's here. And by the way, these radial loads are called W sub r. And there's going to be different radial loads and different tangential loads on each of the gearing. Okay. But W sub t is equal to the torque divided by the diameter over 2. In other words, divided by the radius. Now what torque? Well, it has to be the torque that's in the shaft. Now notice the torque going out this way is different than the torque going out this way. How do I know that? Because the amount of power flowing out at A and B are different, yet the speed is the same. And so there's an equation just above equation 12.1, which will help us out as well. It says that torque is equal to 63,000 multiplied by P over N. Now, let me warn you, this equation is only useful in English units. We're not in English units, so this equation is not going to help us. So what we need to do is just use units directly, and torque is just power over speed. Another way of looking at this equation, you may have seen this before, power is equal to torque times speed. If you're in dynamics with me, you know that power is equal to force times velocity. Notice that these two are analogous. The torque is analogous to the force, and the angular speed is analogous to the linear speed. It's just that torque has both the size dimension in it and the force dimension, whereas force just has a force dimension and velocity has the size dimension. Okay. Anyway, if you understand that, great. If you don't, it's okay. This is what we need. So what we need to do is figure out how much torque there is in A to C and C to E. So let's do that. Now I'm going to transition over and do most of my calculations in Excel. So I will post the Excel spreadsheet. Now if you're watching the video, you'll be able to download it as well and look at it and understand this. We'll do a sample calculation on the board, then we'll fill in Excel and be done with that. Okay? So for example, if we wanted the torque between A and C, what we'd have to do is take 15 kilowatts and divide it by the speed. Now the speed was given in RPM, if I remember right. Let's see, wasn't it 480? I read it and I don't, yeah, 480 RPM. So I'm going to convert that from the very beginning. So the speed at 480 revolutions per minute, I'd want that in radians per second instead. So let's go with 2 pi radians per revolution. That'll take care of the revolutions, and then multiply 1 minute by 60 seconds. So grab your calculator, please, and tell me what that speed is in radians per second. And once you've got it, then go ahead and plug it in and tell me the torque in section AC. Now, while you're doing that, I will go over and calculate it in Excel as well. Okay, so there's a question about the units that we'll get here. We've got a number for our speed. The speed came out to 50.27 or so radians per second. And so now we have to plug in 50.27 radians per second here. Now the radians go away for free. 15 kilowatts is just 15,000 watts. But a watt is just a joule per second. So do you see how the seconds cancel? So if the seconds go away, then we have whatever the number is, joules. But a joule is just a Newton meter. And so once you do all of this, you get the torque in Newton meters. And the torque in A to C that we calculated in our spreadsheet is about 298 or so meters.
Okay.
Okay? By the way, we calculated the torque in the spreadsheet between A and E and got 149 or so Newton meters. So basically the torque over in this section of the shaft is 100 and, what did I say, 98? No, 149 Newton meters. Let's do it this way. We'll need this equation, but we'll just move it down a bit. And the torque over on the left-hand side from A to C is 298. Okay, so that's the first step, is to calculate the torque. And the reason we start with the torque is because we can use that torque to calculate the tangential load. Now, the equation I had just a second ago was tangential load equals torque divided by diameter over 2. Now, I've got you might get confused at this point, because you look at this diameter and you think, well, I'm trying to design this shaft, so how do I know the diameter? Well, we're not talking about the diameter of the shaft, we're talking about the diameter of the gear. Okay, because the relationship between the torque and the tangential load is a function of how far out that tangential load is on the gear. In other words, how big the gear itself is, not the shaft. So we can actually get at the tangential load. So let's calculate the tangential load on E, for example. So we'd have the torque. What torque? The torque in A to E, 149 Newton meters, divided by the diameter of the gear over 2. So we have to look, and there's several different diameters of the gear. There's the outside diameter, where you have the teeth at the maximum height. There's the root diameter at the root of the teeth. But they have given us the diameters, and what they've given us is what's called the pitch diameter, which is sort of the average diameter, and it's what we use for our calculation here. So the pitch diameter on gear E, let's see, looks like it's a 62 millimeter. So 0.62 meter over 2, so that'll take care of meters. And we should just have a load in newtons. So plug that in your calculators, let's see what we get. And then we'll pause the video in the meantime and calculate the rest of the tangential loads. Okay, so we've got the tangential load at E. We went to the spreadsheet and calculated the tangential load at A as well. And at A, we got a tangential load of about 6,000 or so. So at A, tangential load is about 6,000 newtons. And you can see the details in the spreadsheet if you're just watching the video. But we'd like to get the tangential load at E. In other words, at C. Because at C, we've got a gear that's driving this whole thing. And so what torque is it? Do we calculate for the right or the left? What do we do? Well, it's easier than that. All you have to do is go back to the equation that says that torque is related to power and speed. And so all we have to do then is plug in the power that's going in here, the 22.5 kilowatts, so 22,500 watts, divide it by the speed, which I've erased. Do you guys have it in your notes there quickly? I can scroll up in the spreadsheet.
Yeah, 480 revolutions per minute, which is
Yeah, but in radians per second.
50.27 radians.
Okay, thanks. So 50.27 or so radians per second, and we'll still get Newton meters of torque out of this thing. Okay, so that's whatever that number is. If you guys would plug that in your calculator, we'll go ahead for the sake of the video and plug everything in to the tangential load. So while you're doing that, I'm going to write down the equation. We'll just need the torque from this equation, because this will just be the torque at C divided by the diameter of the gear at C over 2.
T equals 447.58.
447.58?
Yep.
Okay, thanks. So we'll just plug that in down here. So 447.58 Newton meters divided by whatever the diameter is at C. So if you guys will go back to the figure and look at the diameter of the gear at C.
300 millimeters.
That sounds no, that sounds right. Okay, so 0.3 meters, which has to be divided by 2. So plug all that in your calculator as well. We'll have an answer for the sake of the video, and then we'll put it in our spreadsheet. So 447.5 or so divided by 0.3 and multiplied by 2.
2983.89.
Now, is it a surprise that the load here is smaller than either of the other two loads? It shouldn't be a surprise, because the magnitude of this load doesn't relate directly to the power going in. It's related, yeah, but you also have to take into account the size of the gear. And since this is a much larger gear than A and E, it actually makes sense that the tangential load would be smaller, because, yeah. And another way of looking at this is, this point on C is actually gonna be moving very fast, right? As you move in the radius and you get to a smaller diameter A and E, then it's gonna be, that tangential velocity is lower, and so basically that's where you get your mechanical advantage and your force can be higher, okay? All right, any questions so far? Okay, well, I'll pause the video, we'll update our spreadsheet and then come back. Okay, so we've got all of our tangential loads at the gearing, and now we'd like to get the radial loads. So the radial loads can be calculated from the tangential loads. They're on page, the equation for it's on page 455, it's equation 12.3. It looks like this. Radial load is tangential load, and a phi. Now, phi is the pressure angle. Basically, phi is what governs the relationship between the radial and the tangential loads. So if I were to draw a line like this, phi would be this angle right here. When we talk about gearing, you'll see more what that is. It has to do with the involute profile and how that's set up. But for now, just understand that this is something that's given in our particular problem. Since we've got 20-degree gearing, that means that the pressure angle is 20. And there's only certain standard angles for gearing. 14.5 is an obsolete standard. But the modern common angles are 20 and 25 degrees. So we've got 20-degree pressure angles on our gearing. So all we need to do is take the tangential load. So for example, if I take the tangent, or I want the radial load at, let's just do C since it's the biggest one. It's the one we were talking about last. I would need to take the tangential load at C multiplied by tan of 20 degrees. And that's pretty straightforward. Now I've already done it in the spreadsheet, so you won't have to do it. But the radial load at C is about 1,100 or so newtons. And you can see the details on the spreadsheet. It's actually 1,086 or so. Okay, so you may want to try this. Just grab your calculator. You've got the numbers. You can see them on the spreadsheet there. And if you're watching the video, you should download the spreadsheet and look at it. Also, there's a SolidWorks model of the shaft that you should download and look at. But and if you don't have SolidWorks on your computer, you can get eDrawings, which is a free viewer, and install it and see what's going on with the shaft. You can take measurements and dimensions and see what it is. But anyway, you should verify that this is the correct radial load at C. Now, I've also calculated the radial loads at A and E as well, since that information is now.
So you take the 1,100 times tangent 20 degrees.
No, you take the tangential load, which is about 3,000 or so, multiply it by the tangent of 20 degrees, and that's where you get the 1,100 from. Okay? Any questions on that? Okay. Now, this is not really a tricky part, but you've got to think back to the statics to understand this. Let me switch colors and go to red. Let's take C as the example, since that's the gearing we've been dealing with. If I draw the shaft itself, now understand, I don't know the size of the shaft yet, but that's okay. If I were to draw the shaft, there are going to be forces from the shaft onto the gear. And the whole reason for analyzing the gear is so that we can figure out the loads on the shaft and therefore design the shaft. So if this gear should not accelerate in the X direction, how much force should the shaft put on the gear in the X direction? WT, right? And so what that means is that the force on the shaft, let me draw forces on the shaft in red, the force on the shaft is WT as well. Does that make sense? Basically, this load just gets translated down.
What do you mean the x-axis? X-axis is like the load.
Let's just say x-axis is this way.
So how's it transmit load?
Okay, let's draw it this way. Let me draw gear C. There's gear C.
Yeah.
Gear C has a tangential load right there. If that was the only load, this body would accelerate this way. So the shaft has to apply W sub T here, but the only place it can apply it is here. You look at it and you say, well, it's going to accelerate. No, it's not going to accelerate in the horizontal direction. It's going to rotate. And that's where torque comes from, is from this force couple.
So your x is coming out this way.
Yeah, let's just take X off this way.
Because I'm thinking like, when I think x, I'm thinking like the rod's going to shift. That's what you Yeah.
Okay, you're thinking along the axial
Yeah.
length. Okay, well, we'd have to decide what coordinate system we're gonna use. I don't care what we call it. I'm just saying summing forces in this direction.
Against the height or whatever.
Oh, here, hang on. This would be good to put on the video. Okay, so here's a gear. The tangential load I'm talking about is a load like this. The shaft will have to apply a load like this. Otherwise, the gear will rotate in this, or it will accelerate. Okay? Now, also, there's a radial load. And it's getting messy, I'm sorry, there's not a lot of space. There's a radial load in this direction, so the shaft has to apply a radial load in this direction to the gear. Or, well, not a radial, but a load in that direction. So what that means is that the load on the shaft is like this. Does that make sense? And its magnitude is WR. So I've gone through a little bit of effort here to just prove to you that these loads essentially translate down to the shaft. And that's the part you need to remember. Okay? So whatever we have, WR and WT, they act on the shaft. Now basically they're going to apply a shear load. To get the magnitude of that shear load, what we need to do, let's see, basically it would be like this. To get the magnitude of that shear load, we just have to add them as a vector sum. So what we need to do now is take W sub t squared plus W sub r squared, take the square root, and there is the shear at, let's say we were looking at C, then that would be the shear at C. Does that make sense? Okay, let's pause the video. Actually, let's plug in the numbers because we've got them, and you grab your calculator. So W sub TC was about 3,000 or so. It's okay to use round numbers, and then in the spreadsheet, see that the number comes out close. So plug that in your calculator because that'll be easier. Because WT sub C is about 3,000, WR sub C is about 1,100. So just square root of the sum of the squares of those two, and we'll see what we've got for the shear at C.
11,401.
11,401. Okay, now that's the total shear.
I'm sorry.
No? Okay.
Yeah, no. 11,401.
Anyone second that?
I got
No?
it.
I got
These are all you got.
You should get something closer to 3,000.
I'll get something
It has to be
different.
more than 3,000.
I got 31.95.
31.95, that sounds reasonable.
Is that 1,100? Oh, that's, I put 11,000.
Yeah. All right, so there's our shear load. Now this is the easy part, okay? I'm going to show you the difficult part in just a second.
31.95.
So let's pause the video, we'll calculate the rest of the shear loads so that we've got them. Okay, so let's continue. Now, what we've done so far is we've calculated the magnitude of the shear at these places, but if you think about it, the direction of that shear may or may not always line up, right? So how do we deal with that? Well, what we normally do is draw shear and moment diagrams. Remember that from beams? I know you may or may not like it, but this is essentially a beam. And so what we're going to do is draw the shear and moment diagrams. Now that we have them, or now that we have the shear loads on the shaft, we can get rid of this. We don't need the power input or output. I wish I had more vertical space because I'd like to have all of these in a line, but we'll just have to deal with what we've got. So normally what you do is you take an axis down the shaft and an axis up, and then what you do is you plot the shear versus position. So I guess let's go ahead and put an x-axis along the axis of the shaft. Okay, and then at A, we're going to have shear in the horizontal plane and in the vertical plane. Okay? Now why are we doing this? We just added the shear together vectorially, so why are we bothering? The reason we're bothering is because we'll need to go from a shear to a moment diagram. Okay? So we need to figure out the direction of all these different loads. Unfortunately, I've erased my diagrams. Let me put it over here because I need this space. What we had was two gears. Here we had a large gear here, small gear here, and let's see, rotation directions. Q rotated in this direction, so all of our gearing rotated counterclockwise from our view. And so the loads on the shafts ended up being, let's see, if it's rotating this way, there'd be force in this direction. So So on the shaft itself, we ended up with loads like this. Okay, let's see, so the force on this gear is also in this direction, so let's see, that would give us a tangential load this way. We'd have a radial load this way, right? Because once again, the radial load always tries to push the gearing apart, and we're interested in loads on the gear that's on the shaft. And we should have something like that. I just need the directions more than anything. Okay, so let's call the tangential plane the horizontal plane, and the radial plane the vertical plane. Okay. Now this problem becomes much more complicated. Well, not a lot more, but some more complicated when the gearing is at an angle, right? Because notice all of our loads nicely line up, right? But if this gear were off at an angle, then both the tangential and the radial loads would change angle, and we'd have to take the vector components to put them into the planes. But anyway, so this will be the horizontal plane, which will be this plane here. And this is the vertical plane. And let me use VERT to make it clear. And I'm not talking about shear, I'm talking about plane. Okay? All right, so now let's plot the magnitudes. If we're looking at the horizontal plane, all the loads are acting to the left. So that's going to make it easy. So if we're to the left of A, there's no shear, but as soon as we get to A, what was the load? Well, it's in the tangential direction, so it's 5968. Okay, so this goes up to 5968 or so at A. Now the magnitude of that shear remains constant until we get to B, but B also applies a shear load. Notice we haven't calculated the magnitude of those loads because we haven't calculated reactions yet. So we'll have to look at a free body diagram of the shaft considering all these loads that are acting. So I should have drawn a load diagram first rather than a shear diagram. Okay. So let's just draw a load diagram, and then we'll get the shear from that. So this is in newtons. Okay, so at A, the load is, what did I say, 5968? At C, notice the load is in the same direction as it is at E, okay? So all my load arrows will be in the same direction, okay? Think about it this way. You cut the shaft like this, okay? And you're looking at it like this. So you've taken this plane and you're looking at it this way, okay? So 5968. Now at C, our load in the tangential, which is our horizontal direction, was 2984. 2984. And at E, the load was 4813. Okay? So now if we want to create a shear diagram, I'm trying to leave enough room for the moment as well. What do? Well, first of all, we've got to get the reactions at B and D. Obviously, the force at B and D is going to have to be, most likely, in this direction, right? Does that make sense? I hope this pin shows up on the video. It's getting kind of light. So what do we have to do? Well, we have to use a sum of force and sum of moment equations. Right? So where would we sum moments? I would choose to sum moments at B, for example. So summing moments at B, I'm going to switch colors in case this doesn't show up on the video. Green seems to be working. Summing moments about B, we know the sum of the moments must be 0 because the shaft is not rotating. So, and they've made our life easy because the distances between all these is just 100 millimeters, right? So that makes it easy. So we'll have, let's see, if we take counterclockwise as positive, then this is going to cause a negative moment. So the distance is 0.1 times 5968. There's our first term. Now I'm going to have to add these down because I'll be off the screen in the video if I don't. But this load here is going to cause a positive moment. Okay? So there's going to be plus 0.1 multiplied by 2984. So far so good? Okay. Tell me how I would add this term. Is that going to cause a positive or a negative moment? The reaction at D.
Negative.
It'll be a negative moment, that's right, because it's gonna twist the shaft clockwise, which is opposite my sign convention, right? So I need to say minus, what distance is there from D to B? Well, each one is just a tenth of a meter, so 0.2, right? So 0.2. How about the load at D? Well, that's the whole reason for writing this equation, right? So let's just say the
0.129.
force at D, whatever it is. Okay? And then the next one, we're going to have another positive term. This one would be 0.3. Everybody see why?
50.1 away.
10, yeah, there, exactly. 100, 100, 100. So 4813. So all we have to do now is solve for FD.
Somewhere around B, wouldn't the first be
Yeah.
negative?
Good question. Would the first be negative? Let's see. Yeah, should be negative. I messed that up. Thanks. Yep. So then both the one with 2984 and 4813 are positive. This one's negative, and
You need
That was
the,
it,
whatever you got it.
I think we've got everything we need now. So if we solve for FD, let's see, what we'd have is,
FD would be 0.1.
let's see, I think we're done with this. Yeah, grab your calculators if you would. What I'll do is I'll just write down 2984 or 298.4. I'll just go ahead and multiply the 0.1.
4813.
So take care of that term. Well, actually, this was a little more complicated, so I guess I should have left it in there. So 0.3 times 4813, that'll take care of that one. And then this term, we'll leave on the same side, so it's minus a tenth. Well, I can do that in my head. So minus 596.8. Now, if I'm solving for it, what I would do is take this to the other side, right? So I would then divide this by 0.2. So add all three of these terms together, 298.4, 0.3 of 4813, and then subtract off 596.8, divide by 0.2, and that should be FD.
Hold on,
I did it a different way, but I want to see if it comes out the same.
Okay. Yeah.
I think that should be positive, not negative.
This one?
Because- Yeah, because you find the moment at B, right?
And find the moment about B.
Yeah, about B.
My sign convention is that anything that causes a moment that's counterclockwise is positive. This causes a negative moment.
Okay.
Good question. So anyone have a number for me from here? You can see why a spreadsheet becomes really valuable in this. There's a lot of calculation. By the way, there's a shaft design module in M-Design, but I don't like it very well. I've tried to use it, it's hard to use.
I got 5,727, but
5,000?
yeah.
How much? I'm sorry, 5,000 how much? Run it again.
You say 57.5?
Yeah. So you got?
How much? 5727?
0.5.
Okay. Now, how would we get, and, man, I messed it up. We just computed it over here, not at B. Okay, so how are we going to get the force at B? Sum, that's right. I would do sum of forces. You could sum moments about here again if you wanted to, but why bother? So if you sum all these and subtract this one off, what do we get? So we're basically just doing a sum of forces in, I don't know what direction. It doesn't really matter. In the horizontal direction.
Opposite direction of the force.
Yeah, opposite of X. Lateral direction. Now there's two lateral directions though, because there's a horizontal and a vertical plane. We'll have to deal with that one.
8,038?
8,038?
That's right.
Okay, thanks. So there are the loads at B and D. Now we can finally make our shear diagram. It looks like I'm going to run out of space. You know what? I'm going to cheat just a little bit. No, I'm not. Okay, so let's see. Let's do this. Now we can make our shear diagram. And the shear diagram will just basically, how do we do this? Do you remember? At A, we go up to 5968, right?
Yeah.
Then we go over to B, and with the delta is what the load represents, right? It's the change. So we've got to go down where this distance is 8,038. So where do we end up on the shear axis? Well, take 5,968, subtract off 8,038. What do you get?
Twenty seventy.
2070?
Yes.
Okay. And that's the same as we go along to C, it remains constant. Now add 2984. It should come out above the axis, but I didn't have that in my head. How much?
914.
914.
I got 5054.
5054
add
wouldn't
that-
be possible. If you
when
take
you add-
2070, oh, I see, it's a negative 2070.
Oh, okay,
So,
no, yeah.
so 2984 less
Oh, yeah.
2070. Okay, so we come back, so I should put a negative sign there. All right, so we come back up a little bit, and then that remains constant, but we have to now subtract off 5727 and a half. So what do we get? That's gonna be even lower than it was before. It's gonna be a negative, a larger negative number,
4813.
4813. You can see, obviously, my graph is not to scale, but we just need conceptually. And of course, then we go over and we get a nice verification that we did it right, because the last number is, or the last load is 4813, which cancels the negative shear. Okay, so there's the shear diagram. Now this is just the horizontal plane. We have to do this in the vertical plane also. I know. These problems are really long. Shaft design, let's see, what all is difficult in this class? Shaft design is difficult because it's long and tedious and detailed. Bearing design is not too bad. There's another, oh, gearing design. Gearing design and shaft design, those two are the biggest topics that are time-consuming, difficult, a lot of stuff to remember. Forgive me for moving over here, but I'm out of board space. And now the important one, now the moment diagram, Newton meters. Now, do you remember how to get a moment diagram from a shear diagram? What do?
Area.
Add up area, that's right, area under curve. So all we really need to do, remember they set up our problem really nicely, right? There's only 0.1 meters between each of these things, okay? So it makes it really easy to calculate. We're going to begin at A with a moment of 0. Now, if we multiply 0.1 times this height, you don't have to do it in your calculator, just move the decimal place over 1. Then at B, C, D, E. At B, we should end up with a moment of 59.6.8, right? Now, then the thing we do is we have to add more area, but this is negative area. So now we have a negative area in the amount of 207, right? So the moment has to decrease by 207. So it doesn't go to 0 by the time it reaches C, but it does decrease. So take 207 from this, and what do we get?
$380, $390. If you round it out.
389.8.
That's fine. Cool. Doesn't matter. Okay. And so then we get to add a little bit more positive area. That's 914 times a tenth, so 91.4 added to this brings us up a little bit. It's too much. So what does that bring us up to? So just add 91.4 to 389.8.
481.2.
Okay, so now we're up at 4. You know what? Let me do it this way. 481.2, 596.8, and 389.8. So we don't have all this mess on the left-hand side. Okay? So then, hopefully, this area will cancel it off. In fact, this area, hopefully, is a negative 481.2. If you look at it, it's a tenth of 481.3, so close enough for our purposes. Brings us back down to 0. Now, you're beginning to see what section of the shaft actually has more load in it. This section of the shaft has a decent amount of moment load. It's actually more than the other places. Okay? But that's just the horizontal plane. We have to do the vertical plane as well. Okay? So let's go through and do it, because what I'm going to do is, I wish I could keep all of these, but I can't. Yeah, maybe I can. Let's put the force diagram in the, in fact, I can move it up just a little bit. Let's put the force diagram, so this is all horizontal stuff. Now we're gonna go for the vertical side. So the force in the vertical side, remember we defined the vertical direction to contain all the radial loads. So now we need all those radial loads that I erased. Now if you remember, when I had the diagram up here, the radial loads were both up on A and C, but down, or A and E, but down on C, okay? So let's put those loads in. I'm trying to stay away from the black pen because it's running out of ink. But the radial loads were 2,000, let's see, 172 or so at A. At C, the radial load was 1,086, but it was in the opposite direction. I'm going to try to fit all of the diagrams here, so let me make that smaller. 1,086. And then at E, the radial load, let's see, was 1,751 or so. Let's round it up to 52. And so now we have to sum moments and forces again at B and D. If you're watching the video, you should probably pause it at this point and try it yourself because you've seen it done once. So I'm going to pause the video, that way we don't run out of video time. And then we'll come back with it filled in.